Okay. Hello. Hello.
Is audible, sir.
Yeah, I'm audible, right? Okay. So before I start today's class, any questions about whatever has been done in the last class and all? No doubts, no questions. So I know that you guys, many of you are coming for the tutorials, which is very good. So I think the MTech CRS people had tutorial yesterday. The MTech CS people have tutorial today, right? So yeah. Yeah. So good. So we were doing graph algorithms, and let me start with graph algorithms today straight away. And I will start with the most okay. So there was graph algorithms, right? So we were talking about graph algorithms, and okay. So of course we motivated graph algorithms in an attempt to kind of say that how do we sort things when there is a poset kind of structure. But we have moved on to graph algorithms, and what we will be doing now is we will take a slightly detour when we'll go into some very basics of graph algorithms, something that people in the coming from a CS background would be knowing, but still we will be spending one class on this, and after that we will see how this is related to this sorting kind of stuff. So the first thing that we will be checking about graph algorithms is a simple thing of connectivity. So if I give you a graph, so input is a graph G. Now, whenever I say input is a graph G, by default, you should assume that this is a adjacency list. Okay. If at all we talk about adjacency matrix, I will mention it clearly there. Okay, so we have been given a graph in an adjacency list form, and I have to output say something like, is G connected? Okay, so now this is not a particularly complicated question. You can say that, okay, what's the big deal about that? But let's think, how would you answer this question? Is G connected? So that means if G is connected, I would have to go and check whether every possible vertex is connected or not with something, with some other. If I start from a particular vertex U is, so I have to check that is for all vertex V is okay. Does there exist a path from say U to V, where U is a particularly, so I have to U is a starting vertex. So that means I have to kind of go over all possible things. So in when we were kids, you sometimes used to have, I don't know whether you guys have played or not, but there are these physical maze kind of structures that are there. Something like a typical so in this in Lucknow and all, which is called Bhulbhulaiya kind of stuff. So you kind of, somebody is hiding somewhere and you are trying to find out whether that person is there or not. Or say if you have just entered ISI, say for that matter, and you want to find out whether a faculty has come to the office or not. Okay, you go and to check at his office, his or her office, and that person is not there. That doesn't mean that that office, that person is not there, right? That person might be have gone somewhere else. So you want to go and check out all possible rooms. You want to check out all possible places where that person can be. So in some sense, what you want to do, both for this kind of stuff and for going over all possible points in the graph or in the connected graph, you want to traverse the graph. So you want to have a particular technique of going over all the possible things in the graph. Now, again, coming back to our notion of this finding out your friend in a maze. Now, if you have ever played this game, you know that there is always a chance of you visiting the same place again and again, or you visiting the same, going along the same path again and again. So what is told that if you are in a big maze, something like the Bhulbhulayas and all those things in Lucknow, if you don't keep a very good documents, then chances are very high that you will get lost in that maze, right? So in some sense, why are you going to get lost? That means you will be going in through the same path multiple times. So when I'm traversing a graph, I will fall in the same problem. I can go over the same edge or same vertex multiple times, and that's not good. So whenever we ask about our algorithm for traversing a graph, usually we have to come up with a protocol in which I say, okay, this is how I want to record how I am going to traverse the graph, and this is how I want to keep track of which all places have I visited and which all places I have not visited. Okay? So that is all that is required when you have to talk about an algorithm for traversing a graph. Okay. Now there can be many algorithms for traversing a graph, and there's a huge number of them, no doubt. But there are two of them that we will be focusing on particularly in this course, and this is almost the two of the most important traversals that you will learn ever almost. So this is looks kind of a simple concept or simple algorithms, but somehow you will see later on in the course that this particular concept is required a lot of time. Okay. Any questions so far? Okay, maybe I can ask you, have everybody of you heard or read about DFS and BFS earlier?
No, sir.
So you guys are not, so maybe I can ask a poll kind of stuff or something. So how many of you, can you just shout out or write a message or something like that, who have not have encountered DFS or BFS? Now, if you have not heard of these two terms, then also you should say that I have not heard DFS and BFS. I just want to know how many of you. So hands raising meaning you have not heard, right? Okay.
Sir, I have heard of those two terms, but that was
You
in
have
our
not.
automata course. This deterministic finite automata, non-deterministic finite automata in this case.
Okay, so but as an algorithms, you have not done it. Yeah. So when I mean as an algorithms, you have not done this. Okay. So I
No,
mean,
sir.
just to kind of get a notion of this thing. So whoever you are saying they have not heard it. So you guys are all from the so you come from the math background, right? So you've given the math exam and coming, or have you given the CS exam, or are you from the CRS?
Sir, math exam.
Mathematics, yeah.
Mathematics exams. Okay. How many of you are from CRS in this? Are there anybody from CRS?
I am from
in this?
CRS.
You have heard of it, or I mean, did
Yes,
you
sir.
see
In
a-
automata, in the course of automata,
yeah,
I have heard
still-
of that.
but not done that. Okay.
No, sir. But that was for the DFA and NFA. Deterministic
that I
finite
understand.
automata, non-deterministic finite. Yeah.
I understand that. So I mean, they have used these concepts of DFS and MNFS, DFS and BFS. Okay. So let me just, okay, now I got the idea. Okay. So let me go over it. Okay. I will try to go a bit fast, but if you have any questions, please stop me. Okay, and so that I can accordingly plan it. Okay, so let me do it. So if we start with the depth first algorithm. Okay, so what's the depth first algorithm? Okay, so maybe I can give some ideas over here. So let me try to put yourself in a so say you have a big classroom. Okay, I can draw a classroom. Here is a big classroom or a room like this. Okay, very weird looking room, and maybe there are some offices over here, and okay, and you can also have some, maybe there's a path like this, there's another corridor, and there's some offices for here. Okay, so is this clear what I have drawn? So this is kind of a corridor, and there's various rooms associated. So you are here. So your job is to go and search out all the possible rooms. Okay, how will you do it? How will you do all the possible rooms? Maybe I can add some more other things also. So maybe just maybe let me add a small other thing that will be helpful. Maybe there is another corridor like this. There's some rooms here. Yeah. So how will you go and traverse these various rooms? And there's no unique way, right? The first one thing can you say, okay, I will just go and find out first room. Okay, then I will maybe go into that more direction as the second room, third room, fourth room. Okay, then fifth room, sixth room, and come back. Or somebody says, okay, I will just take the first room. Then I will look at, okay, if it don't find it, I will just look at this room. If I don't find something here, then I might go into back here and look at the second room, and so on, right? There are two various different ways of finding the rooms or going into the various rooms. So the first one that I talked about is like, okay, I want to go and search all the rooms till I have nothing else to do but to retrace back. I have not looked at all the rooms. I have looked at all the rooms that I found in the way. Now I can retrace back and then say, okay, when I find another intersection, I will go again here. And I say, go and find out all the rooms, and then I hit another boundary, another. Then I come back, okay, fine, here I can go for another room, and then I understand what's going on, right? So in some sense, this is what this kind of a searching is called a DFS. I will of course define it formally and all of them, but this is the intuitive thing, that you go into the depth as much deep into the graph as you can. Okay, so you have a huge graph, say, okay, some huge graph is sitting there. Okay, say something like this, and you are here. So this is the starting vertex. Okay, so the first thing you can do is that you can first check this vertex, and you are finding some, you have to go and visit all the vertices. You can say that, okay, I'll first visit this vertex, then I'll visit this vertex. I will then I go from here to the next one, 3. Then I go from here to the next one, 4. Okay, so maybe I can add a few more things over there.
Is there a reason for you to choose when you have to make a choice which path to take?
No, not exactly. But whether I am going to choose this path or this path is something that is not fixed. Okay, that is one thing that I can decide. But more importantly, what I am trying to say is that instead of me trying to, after I have seen the first vertex or this after I have seen the second vertex, I could have told that okay, now I don't want to go further. I want to just first check all the vertices that are okay. There's nothing in 2. Sorry, I have found 1 to 2. I have not seen anything. Now let me go back to 1 and say that okay, see, did not find anything in 2. Then okay, 1 has another one. Okay, let me go here. Instead of doing that, what I am proposing is that you go as far as you can. You can choose. Okay, so once you are in, so you are here. Maybe I can try to do some animation. You are here. You go here. Fine. Then after that, you have 2 points. You can either go here or here. Fine. So I said, okay, let me go. So let's say maybe you can say, okay, I will go here. Okay. And I said, okay, I've seen here, there's nothing here. Now where should I go? Then this will be the third vertex. Then okay, I can go here. Okay. Okay, fine. I will go and look at this vertex. Is there anything here? No. Okay, so this is the fourth vertex. Then I go another one. Okay, and this will be the fifth vertex. See, I keep on going. So I kind of went from 1 to 2, then 2 to 3, then 3 to 4, then 4 to 5. And I have kind of gone as much as I could have run, right? At that time, I am getting stuck. Okay, that time I have to decide, okay, let me now, go back. Okay, and that means now this will say that, okay, see, there is nothing else to go. 5 doesn't have any more neighbors, so I can come back to 4. And at that time I can say that, okay, but at 4 has some other neighbors, right? I have not done that, so let me go to that. And you can look at this, and that will be the 6th vertex that I have found. Then I can again say that, okay, 6 doesn't have any more neighbors, so I need to go back again. At any point of time going back to it's the one from which I have come, right? And that time, what should I do? Can somebody say what should I do?
Go to 1.
Go to 1. See, from here, what you are seeing is that 4 has another neighbor. So 4 has another neighbor is there, but you don't know which neighbor is it. So in some sense, you have to go and check which neighbor is it, right? Okay, may not be physically go and check. You have to go and look at it in the correct in the place of the adjacency list. Which node is it? And in some sense, intuitively, what will happen is that you will go to 1. You will see that, oh, see, 1 is already marked red. So that means I have done with 1, so I don't need to worry about it. So in some sense, I will go over this particular path, but it will not successfully find anything. Okay. Then I will say that, okay, does 4 have any other neighbor? No, 4 doesn't have any other neighbor. So let me go back to the one thing that I came from to 4. So I came to 4 from 3. Now I say, okay, see, I have used 3 has 2 neighbors, of course, 2 and 4, but they have already been used. So does 3 have some other neighbor? Oh yes, 3 has another neighbor. I can take that path and go to that neighbor. So I am basically taking this path. And in that case, this will get found and this will be 7. Now, okay, does 7 have some neighbor? Yes. And I'll go to 7. Here, 7 has a neighbor. And I'll be using this node to find this vertex. So this will be the 8th vertex. Now at this point, it will ask, does 8 has something? And yes, 8 also has something. But 8, I will go to that neighbor, find that, oh, this neighbor is already been colored or I've already visited it, so it come back. So this is exactly kind of that I will be walking down this path, but not to find anything. Similarly, will be this path. I will be walking down this path. So at this time, I have come to a point, I'm in a vertex, and I can say that, okay, I'm in this vertex, and this vertex doesn't have any more neighbor to be found. So there no new unexplored neighbor. So at that time, I have to kind of go back and talk about go to 7. And then from 7, is it does 7 has some unexplored neighbor? Oh yes, 7 is an unexplored number. I can go here. Ah, okay, good. And this will be the 9th vertex. 9 doesn't have any other unexplored number. I will go back to 7, and then I will go to here, and then okay, I will come to here. So this will be the 10th vertex, and then from here I will go to here, 11th vertex. And now, what? Where am I? I am here. So at that point, I don't know anything, right? It's a huge graph. All I can say that I am now in a vertex in which I am stuck. Basically, it doesn't have new unexplored neighbor. Fine. So in that case, just like earlier, I should go up to the previous one, which is 10. Does 10 have some unexplored neighbor? No. Okay. So then I should go further up. Okay. Does 7 have some unexplored neighbor? Now it turns out the 7, we have kind of seen all the neighbors of 7. So 7 doesn't also have an unexplored neighbor. Okay. Now let me go back to thing that from which I came. So 7, I did not come from 8. I came from 3. Okay, does 3 have some unexplored neighbor? What do you think? So
No,
it
sir,
turns
it
out that
doesn't.
it doesn't have. I mean, assuming that we have marked it out carefully, that when I walk down this path, I also marked out this path. If I had kind of done that, in that case, I have taken care of this neighbor also, right? So in that setting, we should go back to 2. 2 doesn't have an unexplored neighbor. Then come to 1. Does 1 have any unexplored neighbor? It says no. And at that time, I have started from some place, which is the root. Okay, so remember this was the root. Okay, and I have explored the graph and come back. So this is a traversal. Now let's try to understand what all things did we need to keep track of at all point of time. So the main idea was that we just keep on going further as much as we can till we get stuck, right? So the few things that we did, what all things did we keep track of? Can somebody tell me one by one?
The vertex which are explored.
Yes. The vertex which are explored, we colored, right? The vertex explored are colored. Okay. Number 2.
The place, the vertex from which we came to the current vertex for the first time.
If the kind of the parent, right, of a vertex, right? It's the vertex from which I came, right? And actually, in some sense, this is all that is there. Okay, so once you
Sir,
have
Is
this,
this,
yeah,
is this a correct statement? Because of the first point, you will never have cycles in this graph, so this will be a tree when you'll the ones that are hard colored red. Is that a correct statement?
hard colored red will be a tree. That is very true. The edges that helps us to find the new vertices, they form a tree, and this tree is what we call as a DFS tree. Okay. So this DFS tree will have lots of different properties. Okay. So okay, so good. So before we talk about the DFS tree, we should understand this thing. So we need to keep track of these two objects, right? And how can we keep track of these two objects?
Sir,
Yeah.
you are telling that it is a traversal, but we are not traversing all the edges, right? 1, 4.
We are traversing all the edges. Why not?
Oh.
Which edges are not traversing?
At 4, when we are going to 1, then we are coming back. We are not going to 1 by that 4, 1 edge.
We are not going to 1, but we are going to kind of I mean, we will look into Ford's adjacency list, neighborhood list. I will check, okay, how so what is the neighbor of 4 that I have not looked at? Oh, it is 1. Okay, but 1 is already colored, so I come back, so I don't look at it. So this is how I will be doing it. So of course, see, I mean, whenever you're doing it, you are not going to draw a graph and moving yourself from one place to the another, right? But you will be going over, so every edge is stored in the adjacency list, right? In a particular place. So for example, this in the adjacency list here, so there's 1, 2, 3, 4. The 4 will have something, right? What all the things that are 4 has 5 and 6, 5, 6, and 1. So and 1 also will have what? 2 and 4. So this, so you can think of the edge is here. The edge is represented. This 1 and 4 edge is represented in 2 places. Once here and once here. This is the edge representing 1, 4. This is the a part which is representing 1, 4, 1. So we will be when we are dealing with the 4th vertex. Okay, we will see that. Okay, let me go down over all the possible the neighbors of 4. Is there any unexplored neighbor? So first we will go from 4 to 5, then okay, then 5 will be ticked, then 4 to 6, then 6 will be ticked, and then I'll have 4 to 1, but 1 is already ticked because of some other reason, and that's why I will tick it here. So I will basically be going over the whole graph. So is the traversal idea clear?
Yes, sir. Okay.
Okay, so of course we are not
Sir,
going to traverse it
Sir,
physically,
what's
but
the
yeah.
need to come back to the vertex where we started from?
Else how will we know whether there is some other edge left or not? So for example, I could have had this thing, right? This could have been a graph. In that case, after traversing the whole thing, we are saying that okay, I've come to 11 and I'm done. But I have
No,
not looked at it.
If we know the total number of vertex and the explode number of vertex are matches, then we have
Okay, so
we
that
have
is
explored
another
all.
way that you can stop it that way. But in that case also, you will not be traversing various edges. Maybe there's an edge over here,
Yes, yes.
or an edge not over here, but something else. The edge over here. That edge has not been traversed. Okay. So I mean, actually, it will not be useful, but we will have to go over that thing, right? And also, as you just told, here the algorithm that I described does not need to know how many nodes are there. It can just simply go and do it. Okay. So this is so let me tell you one place where this kind of traversals are very much required. Right? When you search something in Google, how does Google find out all the places where that particular search matches? So if you search, say, algorithms in Google, then it will give you all the possible places or websites where the word algorithms comes in. Right? Now, how they order it, whether the first choice is an algorithm or not, that's a different issue. They use some other technique. But to go and find out all the possible places where the word algorithms is going, they go from a node, various web pages to various web pages. Okay, every node in that case is a web page, and an edge is basically if this web page has a link to the following other web page, then there is an edge. So this is called a web crawler. Okay, it starts from somewhere and it keeps on crawling the whole web and finding out all of it. Now, of course, Google should not be knowing how many web pages are there. That's a huge number and very hard to kind of keep track of and all. Right? So a traversal would not require you to know how many edges are there. It is just looking at this graph and just continue. Is this clear? This one? Let me go over this depth first search thing. Okay. So here is an another graph on which I will be doing the depth first search once again. Okay, so I will start with the vertex A. Now, I told you here that we need to have a particular concept of this something to store these things, right? Now, the first one you can say that how can you store it, right? How can you store the first one? You can just add a color in the adjacency list. Now, the other one also you can do it in various other ways. You can actually go and try to maintain it in some other way. But one thing that often is used is what is called a stack. Now, if you have done automata theory, you have used stack already in the. Also, you guys are doing automata right now, is it? Hello.
For CS automata courses in this sem, it's ongoing right now. For CRS, I think it was done in the last semester.
Oh, okay. So the concept of stack is something that you will, if people who have done automata, will see it in the context-free languages or the push-down automata thing. The idea is that you are going to, whenever some object comes in, you want to put it there. The B comes in, I put it there, and you just put it like this. So this has to support two operations. It's a push operation. So you have a stack, okay, and you push any element, push A, then say push B, then push C, kind of stuff like that. Then you have another operation which just says pop. Pop basically just takes out or returns you the last element on the topmost element. This pop. So something like, so if you want to now, so pop. So right now at this point, pop would have given you C. Pop would give you, now if I put another pop, I would get B. Okay. Then I can have a push D, then it will push D over here. Then I can have push, say I push back C again, then I will put a C over here. It's like a stack, right? And then pop will give you the topmost element. Now, this is another thing that I would like you guys to go and write a code. Okay, write a code, either a C code or a Python code, doesn't matter, for implementing push and pop. Okay, so this is a stack. Have you done it already in your data structure?
So we have
Yes.
done this in C lab for CSP.
Okay, so if you have done it, then very good. If not, you can do it again. Okay, so I will show you how you can use this stack to implement this depth first. Okay, so whenever you are here in a particular node, you push it. Then you look at its neighbors and look at anything. And at that point, we are coloring it. So you can see this one, there's a slight difference in color from this thing. This is blue and this is gray. Do you see this difference in your screen?
Yes, sir.
Yes, sir. Yeah. So A is colored red because this is just to kind of keep a track of that this is the root node. That's it. Okay. So it will we color it blue and we push it. Then I again color it. I look at this another neighbor which is E. I color it blue and push it. Then I look at another neighbor. I color it blue. Now at any point of time, what are we doing actually? Let me just quickly go back here. So what neighbor we are looking at? See, all that we are storing is here, right? And this is written in the adjacency list. So we are looking at, we have the stack. We will be basically popping this or looking at the topmost element here, right? Oh, okay, the topmost element is A, no problem. In that case, what is the neighbor of A? Give me one neighbor of A from the decision from the neighborhood list, and then I go. Now I come to B. B is in this stack. Okay, what is the neighbor of B? Okay, so I'll always be looking at the topmost element, right? And neighbor would be one of them will be E. Okay, great. Now I'll be looking neighbor of E. Neighbor of E will be C. Fine. Now I look at neighbor of C. And the neighbor of C can give me B here. But I also have this coloring, right? So I looked at the neighbor of C, which is B, and B will be okay. We have it is already colored. So I am done. Good. So now give me another neighbor of C. Right? Another neighbor of C, that means it will be H and push H. Now H has no neighbor. So when I ask for neighbor of H, I have no other thing. So I should pop out H and color it green. And that means I am done with H in some sense. That I am not going to revisit H again. At that time, look at the stack. Surprisingly, the stack automatically contains the parent of H. The topmost element is always the parent of the last one that we have found. Okay, so C will also have the same thing. We will have no other neighbor. Done. Now, okay, let me ask you here. How is C doesn't have any neighbor? Think of it from an algorithm's point of view. C has a neighbor, right? Which is E or B. What will you do? How can you? Yeah. So the idea is that when
Sir, I
we
didn't
look
get
at
the question. Sir, I didn't get the question. So can you
Okay.
explain what is the
in the
question?
adjacency list, C, B is in the adjacency list of C, right?
Yes, sir.
But at this point, when I ask, what will it return?
Sir, the flag, the color flag of P is turned up because it has been
Yes,
visited.
but in
the
that case, I have to go and revisit. I'm going to check that one again. Is it?
But your stack already contains the information where it came from, right?
That comes from the information that it came from, but
Right,
B is
right.
not B is there, but much lower down. So at this point, if I look at this stack, okay, it doesn't immediately shows me a stack or the colors it doesn't show me that this CB has been looked at. The CB edge has been looked at already.
You have to check the color flag of B,
So
all the neighbors of C.
yeah, that is, but then that will cost me again, right? I've already gone over C to B again once. So I don't want to revisit this B from C multiple times. So one way is to just kick out B. Once we have seen B, I just kick out B from the neighborhood of C. In the adjacency list that I have, the neighborhood of C, I will just throw away B. Okay, and in that case, I would never be required to look back onto B. So when I come to C now, at that time, C doesn't even have a neighbor of B in some sense. So this is just a bookkeeping thing. Okay. It is something like, say you have a book where you have written down names of all your friends who have borrowed books from you. Okay. Friend 1 has borrowed book 1, friend 2 has borrowed book 2, friend 3 has borrowed book 3, and so on and so forth. Right? Now, if I tell you that who has borrowed book or has friend, has the 10th friend borrowed anything, then you have to go through the whole book and find out. Right? But issue is that now it's a book that you are maintaining for life. If your first friend has returned you that book, what can you do? You can write down in that paper that, okay, this first friend had borrowed this book and has returned me the book. But then when you are looking through the book, you have to read that page. Right?
Or I can erase that he has borrowed that book.
Or you can just, yes, erase that part, or just clear that page and throw it away. Right? That saves time. And this is exactly what we will be doing. Once we have visited B from C, I am done with B.
In your strategy, are you creating another copy of the graph neighborhood?
Right? Sorry? Sorry, can you repeat once again what you said?
In your solution, are you creating another copy of the graph?
Okay, for now, let's say that we have created a copy of the graph. But I mean, that also we don't need to do it. We can keep it in another bookkeeping kind of idea. Okay, but at least, yeah, so let's start with that. We have a copy of the graph, which you can destroy if required.
Stack, like, is the neighborhood of a vertex another stack?
No. Neighborhood is the array, right? Because we are dealing with the adjacency list model. Right? The neighborhood is an array. Yeah, so we'll see how you want to implement this one. But basically, you want to, yeah, hello.
Yes, so I understood the updation procedure to avoid repeating edges, but I probably missed the traversal from where, at which point did we go from C to B? When was this edge covered in this traversal example?
Okay, so maybe this is something. Okay, here right now at this point, again, this is something that can you see this edge?
Yes,
this edge will suddenly become a bit bolder.
Yes. But then we are not going to B.
We are not going to B, but we are spending a minute there, right?
We are not going to B because then the DFS would have gone to D from there, right? So just because it was covered earlier, we are not.
We are not going. We are not doing anything, but we are going over the edge in the sense that we are seeing the place where this edge is stored. Okay, B is the neighborhood of C, but B is marked blue. Therefore, we don't need to go there. We are all doing all of these things, right?
Okay, sir.
So this set of things we don't want to do multiple times.
Okay. And another thing, when we are updating, suppose we are traveling from E to C, we are updating the adjacency list of E and removing C from it.
Yes.
Are we also removing E from the adjacency list of C
Okay,
at the
so
same
that is
time?
also, that is a good point. Whether you want to remove E or not from the C is something that we can have a discussion on that. But even if you don't do it, it's just a double the cost. You possibly will go from E to C and C to E in
Yes,
two
yes,
places.
yes.
Okay, so it's not too much of a cost. It will only be a multiple of 2. You will
Yes,
traverse
yes,
every
yes.
edge twice. So I'm not really going to worry about that much. Okay.
Okay, okay, sir.
Okay, so the one thing that is there in the stack is that, I mean, look at it here. Okay, so this will be fun. With C we have E. Okay, now and with E, now I ask what are the other edges do I have, and then okay, it picks up something, the F. Now, okay, does F has some other neighbors? Yes, F has a neighbor D, and D has a neighbor. Okay, so D has one after another 3 neighbors. So we'll not do anything in each of them, but except that we will kind of have to go over them, D of A, D of B, and D of C. And at that time D is done, so I will color it green. So what is the thing that we came from? D is F, right? So I come, so okay, D is removed and we come to F. Now, see, note that here, surprisingly in this stack, every time, wherever we are now, okay, so that one is, so one we are F, right? The one right below F is the vertex from which we came. Okay, so from F I go to G, and G we will look at the G to E, and at that time I will be done with G basically. So G will be popped out, G will be colored green, and I come back to F. F doesn't have any other neighbor, so F will be popped out, F will be green, and I come to E. See, just like we were supposed to go to E, right? Because E was the one from which came, but that is just written in the stack top. So this is a thing that I would not prove it. I would like you guys to prove it with the very discrete math kind of stuff like that. That proves that in this kind of a DFS argument that we did, the topmost point, okay, or the stack has this property that at any point of time when we are popping out something, sorry, going to pop out something, the one below this next is the parent of that vertex. So in stack maintains the parent of the vertex. Okay, so at this point we will be done with E, B, and then we go to A. And when we stop, that we stop when there's nothing else to be done. The stack is empty, and at this point we are done. Okay, so this is the DFS algorithm. Okay, so we have to have the stack where we kind of want to do the two things, the push and the pop. And this is the pseudocode. Let's go over it once quickly. Okay, initially we color all the vertices gray, then start with pushing the vertex from which we want to do the DFS, that's the start vertex. And now we keep on doing it till the time the stack is empty. Okay, at any point of time, I first pop the S, look at the topmost vertex. When I pop the vertex, topmost vertex, if the neighborhood is empty, then I will color green and done. If the neighborhood is not empty, so if the neighborhood of U is some W, there is some W, then what do? I would say that okay, and the color of W is gray, meaning I have W is not visited. Then at that time I would color the blue, remove W from the neighborhood of U, and push what? So U has been popped, but you are I'm not done with U, right? So you push U back, then push W back, and okay, we have this kind of separate thing, select UV, which is basically the edge that was colored red. Okay, okay, there's one more step that is not written up, which is that what happens if it is not gray. Okay, so I have so there is a small thing that I forgot to write. So you can complete this pseudocode. That this line, what happens after you take the W from this one? What happens if the color is not gray? Okay, so that means it has been visited already. So in that case, of course, we will not be selecting anything, but we will just be doing a push. I will put back the U back on the topmost.
Sir,
Yeah.
Yeah. Just one query that we were assuming that the algorithm does not require us to know how many vertices are there initially, citing the Google
Correct.
example, right? But the initial coloring to gray, that in some sense requires us to have a knowledge of all the vertices that are there, right?
Okay, so that is something that, so this is something we were done it, but you don't need to color initial color gray. Okay, you can think of that as all the colors are empty or something like that. When you do an actual
Yeah, yeah.
implementation, you don't need to color everything gray. No color is a gray color, you can think of.
Yes, yes.
Okay. Okay, so again, so I would like you guys to go back and not only work out the details of the stack, but also maybe try to write down the DFS properly for yourself once. Okay. Now, what is the running time of this algorithm? Now, here as it is written there, every edge is visited twice, and each vertex is of course visited. So the total running time is nothing but order V plus E, which is, as we remember from the last time, it is exactly the size of the adjacency list. So the running time is linear. Okay, we have not done anything non-trivial over here. This is a very simple algorithm, right? We have been given a graph and we are just going to visit all the edges and all the vertices in a organized way, so that we don't go in loops or circles. That will give us something that will make us waste a lot of time or something.
Sir, is this time complexity independent of your starting point?
Time complexity is independent of my starting point. Okay, I mean, so depending on the starting point, it would I mean, as long as this, so the time complexity will be just be order V plus E. What is the V and what is the? It is this connected component. It is the size of the connected component of the starting point. Note that I would not be visiting any vertex here if there is another component which is not connected to A. That component will not even be touching, right? So we will be only be stuck with that connected component only. At least the way in which I have presented this DFS, that is it. There are some other ways of presenting the DFS in which you go component by component, one by one, and keep on doing the DFS. But they're kind of yeah. Now, okay. So of course, the DFS can be used to check whether the graph is connected or not, right? And whether the graph has a cycle or not. As soon as we come up with we see that one of these edges, which is going to another vertex which is not gray, already we know that, oh, there is a cycle. Okay, If you have not got, you don't really immediately see this one, think about it a little bit and you will see it. Okay. As one of your friends has already pointed out, that this set of selected edges is a spanning tree. It's a tree that spans the connected component of the graph at least. Right? Now, why will it be a tree? Because again, we are not going to visit anything new. So every vertex is being visited only once, right? So there cannot be a cycle there in the set of selected edges. So these are the three very simple applications. There are of course a lot more applications, but if somebody comes up and says that, okay, produce me a spanning tree of a graph, yeah, run a DFS, you get a spanning tree. Okay. Now the DFS tree has some nice properties. Okay. Okay. So let me draw a couple of trees and let me ask you guys. So say if this is the graph over here. Okay. So say, so these are the red edges. Okay, so these are the edges that we have used on the tree. Okay, so these are the red edges they are used in the tree. So these are called the tree edges. But in the graph, there are also the other edges, which are the maybe I will use the dotted edges, right? Dotted edges like this. Okay. Now these are usually the graph has three kind of edges in the undirected graph. First of them is the red edges, which are the tree edges. Then what we have the back edges. Now what are back edges? So back edges are edges that are from a, I mean, back edges basically, or back edges sometimes also forward edges. I mean, of course, there are the concept of, we can also talk about the same concept in the case of directed graphs, but it is between a vertex and its ancestor. So something like this. This is vertex and its ancestor. Okay. And then there are the cross edges. So what are the cross edges? These are everything other than these two. For example, this edge is a cross edge. This is between two brothers or two siblings. This is between cousins, right? So they are not to the ancestors. Now, look at this graph. Okay. And let's start with, let's say that this was the root node. Do you think this, I mean, the DFS algorithm could have produced this graph? So this is the whole graph. A DFS algorithm was ran with this vertex and it produced this tree. Do you think it is possible? Whatever, nobody is answering anything.
No, sir. Like the cross edges that we have here, suppose at the left, bottom left corner, yeah,
Right.
either of those two being visited would not have returned to their parent. Rather, there is an open neighbor that
Right.
the node has, so it can
Right.
be produced by DFS.
So,
There cannot be any cross
out of
edges.
these two, let's assume that this one was visited first. Okay, just for the sake of it. So at that time, how would the graph be looking like? So there will be no edge here. At that time, the graph would be looking like this, and there's an edge from here. In that case, the DFS algorithm cannot say that, oh, I don't have any other neighbor. DFS will have a neighbor like this. In that case, this vertex would have been explored from this edge, not from this edge. Right? So in that case, the graph, if we had done, the graph would have looked like this. And in that case, this edge would have become dotted. Is this clear? Okay. Let's see. Amit Bhumik. Hello.
Yes, sir.
Yeah. So have you seen DFS BFS earlier?
No, sir. I just.
Okay. Is this clear that what's going on here? That this
Yes, sir.
cross edge cannot be there?
Yes, sir.
Okay, so now can you tell me why? What about this edge? Will this edge be there? Can this edge be there?
No, sir. This has also not be there because we are already checked it.
Because we have already checked it. What do you mean? So just for your help, let me write down. Let's call this one W. This is called V, and this is called X and Y. Yeah. Now, can you tell me why will the edge this VW cannot be a I mean why this cannot be a DFS tree?
Sir, if we first check the XU, then again return to U to X and X to the red mark vertex and then to Y and then to W. In that case, UW will not be there.
Yes, but will that happen? That's what I'm asking. Will DFS algorithm do that? So you are saying that okay, at some point of time, I am here, right? At that point, says this red edges has not been picked up. Say at this time, this thing has not been done. Let's say this is a blue, this is a blue, and at that time, there is an edge over here, and there's an edge over here also, and I am standing here. I have just finished reading V.
Sir, in
Yes,
that
I'm
case, I will go V to W.
In that case, go to V to W, right? So
Yes,
that
sir.
means I cannot go back to X.
Yes.
So what you are saying is not possible. The graph has this the VW already, right?
Yes.
So
Yes, sir.
when if I'm seeing tab V for the first time, I cannot go back to X. The algorithm cannot go back to X. The algorithm has to then look at W.
W.
Okay, and then it
Sir.
can possibly go something else also. Okay,
Yes, sir.
so
Then
basically, in a DFS algorithm, these concepts of cross edges cannot be there. There can never be cross edges. Okay, so there can be back edges or forward edges and free edges. Okay, so is this clear? This whole thing? Okay, so if it is clear, then let me just quickly go over a few more things here. First of all, just like I did it for the case of undirected graph, we can do it for the directed graph. There's no difference whatsoever. So for example, here I am doing a DFS from say H, and of course you are going only along the directed grid. And there's an animation here that kind of will tell you how this happens. Like for example, I start from H and I go to A. At that time, A doesn't have any other outgoing edges. And at that time, I should be kind of done with it. And I do the same thing. Okay, I mean, keep on doing it. At some point of time, I will be done. So when you do a depth first search, you can do it also on a directed graph. Okay, so this can also be, of course, be used for kind of checking whether there is a directed path from a particular vertex to another vertex. And okay, the kind of edges. Okay, here in this case, in the case of this one, can there be graphs like this? Let me just. In the case of directed edges, okay, so this is the directed graph. Okay, so let me again draw it. Okay, so whenever I'm drawing these dotted edges, so these are the edges that are not in the tree, not a tree edge. And the bold edges are the ones which are tree edges. Okay. Okay, so now let's see. If this is the node, which of the edges is the problematic edge, do you think?
So those which are on the same level and the dotted edges are being connected. So the left hand side ones.
So this edge is this cannot happen, is it? That's what you're saying.
Yes.
That
Similarly,
can
one
happen,
above
I
it.
think.
Similarly, one above it. Yes, your friend are not agreeing with you. So why
It
can this
depends
edge
on
happen?
it depends on what vertex we visit first.
Okay, good. So let's say if this is the vertex 1, I mean in terms of the visits, okay, which of them has visited first? So 1, 2, then 3, then 4, 5, 6, 7, 8, 9, 10. In that case, what happens? These are all numbered in terms of which have been discovered first. Okay.
Sir, if
In
I
any case,
go
we'll
from
always
2 to
visit
3,
2, 6, right?
You will always visit 2, 6. Okay. Why?
Well, it's a neighbor. Like when you go first to 2,
Yes. When you
then you
go
have to
first to
visit
2,
6. Then you have to visit 6,
so
right?
before we go back to 1, you have to check out all the possible neighbors of 2, and 6 would be visited there. At that time, 6 was not visited, right? So this edge cannot be there. Is this clear that this edge cannot be there because of this? Okay, very good. What about this edge?
Here it is dependent on your choice. If you first went to 3, then you have to come back since the direction will force you. And then you can
Yes.
go to 4. But if you first go to 4,
Yes,
then it
so-
has to occur.
Yes. So if 3 is first discovered, at that time 4 was not discovered, then who cares? I cannot find 4 from 3 because 4 is not a neighbor of 3, out neighbor of 3, right? You cannot have an edge from 3 to, you don't have an edge from 3 to 4. So I will go back to 2, and then 2 will say, oh, now go and find out 4, and I will find out 4. But if I had gone to 4 first, then that would have been different. If I had gone to 4 first, then from 4 I should have been able to find out point 3, and I would have visited 3 through 4. So in some sense, what I'm saying is that in a case of directed graph, yeah.
Similarly, if we had visited 6 before 2, then that edge could have been there, right? 2 to 6, that is that you
Right,
mentioned earlier.
right,
Yeah.
exactly.
Like any of them can be
Right,
there. It depends on the traversal.
Right. It depends upon the ordering. Okay. So you cannot say. So in the case of
No, wait.
directed,
Sir,
even if you visit 6 before,
Yeah.
the line that you draw was a dotted line from 2 to 6, right? Regardless of have you visited 6 before or not, you'll have to check it, right?
No, you like if it is like this, right? If you have visited 6 before, from 6 you cannot find 2 because it's a directed range. Say I have not at that time I have not seen 2. I have just seen 6. In that case,
I
2
see,
is
okay.
not in the neighborhood of 2.
I see. Yeah,
2
understood.
is not in the
Understood.
neighborhood of 6,
Understood.
right? So it depends upon the cross edges can be there, but that depends upon the ordering. Okay, so you cannot flat out say that cross edges cannot be there. So cross edges, tree edges, and back edges, all of them are possible. In fact, there can be forward edges also. Okay, and of course, if there is a back edge, okay, good. So at that now, we were talking about finding cycles. Cycles can only happen when you have a edge like this, back. A forward edge doesn't give you a cycle. So for example, if I remove this particular thing, then this is a possible DFS tree, right? But here, this doesn't form a cycle. So this is just this is one direction. The only cycle that can be formed is like this. Okay. So a back edge will give you a cycle. Now you can go and prove that if a directed graph has a directed cycle, then there has to be a back edge. Okay. Okay, so this is not actually prove that there has to be a back edge. Okay. Okay, the runtime of this directed case is also linear. So that's not a big deal. That means exactly the same. Okay, so now let me come up with this thing that we had talked about in the last class. Okay, so this is an application of this depth first search. So let's us have this kind of stuff that I have some 8 jobs, and there are some set of rules there that A has to be done before B. It's a POSET kind of stuff. B has to be done before C and D, C, D, and E, and so on and so forth. Various POSETs are there. So all these relationships can be written as a tree, as a graph, right? I can look at all this. I can define these various nodes, 8 different nodes, and I can draw these edges. Like if A is before B and D, that means there will be an edge from B to A and D to A. That means an edge, directed edge from some vertex to another vertex means the starting node has to be done before the finishing node. And in this way, say if you just draw this kind of an example, you can make a whole graph out of it, right? And the goal is to order this vertices in such a way that if Vi is an edge, then I must be less than j. Right? Vi Vj is an edge. So that means we can say that okay, first do B A. So I should not say that okay, do A then do B. At whatever way, I have to kind of tell that okay, do maybe H first, then E first, then G, then something, and so on, such that everything can be done properly. Okay. So this is what is called topological sorting of a graph. So you have a topological sorting of stuff. Of course, I have to assume that the graph does not have a cycle, right? Yeah. So I have to assume that the graph doesn't have a cycle. That means it's an acyclic graph. In an acyclic graph, you know that there exists a vertex that doesn't have any incoming edges. At least one vertex, maybe more. Okay. In that case, find a vertex that has no incoming edges. And do this following thing. You start from this. So in this case, this incoming, that vertex is say H. Start a DFS from H. Now, when we did this DFS, we had this coloring, right? We started with gray, then we went to blue, and then we went to red. When red was the time when the vertex is done. It's a finishing time. Okay. And in that respect, you ordered them according to when the vertex was colored red. So that means that according to when it was done completely. Okay. So basically here, if you do this topological sort and we have these various things, see, I mean, at this point, A is done. So A I am writing here. Then I go to B. At the time, B also is done. Then I go to E, but E is not done because E has an edge. So I go to D. Then D is done. D looks at all of them. So D is done. And then you go to E back and look at this thing. Then you have C, which is done. At the time, we come back to E, and E is done. E doesn't have any other neighbor going out of. So E is done. Then you go to G. So G is not done. So you have to F. So you finish F, then you finish D, then you finish H. And note that this ordering, I claim, is a possible topological sort of the graph. Note that this is not the unique one, but it is a topological sort. So that means we first do H, then do G, then do E, F, then do E, and so on and so forth. Right? Then C, then D, then B, then E. Okay. Now there are two things. Of course, this is not the unique thing that I told you. For example, I could have swapped C and D here. I could have done first D and then C, and then that would also be a topological sort. It would have not violated anything. So this is not, but more importantly, this gives us a topological sort. Now, why does it give us? Can we prove that why does it give the topological sort of this algorithm? Maybe I can ask you guys to
So
think a little bit.
the graph which we end up getting is a tree, which is under directed tree.
Right.
Therefore, it's a directed acyclic graph, and therefore
Right.
we know that if we can label a directed any graph, if we can label it in such a way that it has a topological sort, then it will be a directed acyclic graph, and the converse is also true. So you're using the converse. But if it is a directed acyclic graph, any labeling would correspond to a topological sorting.
Okay, I mean, you have used a theorem or a problem which had all the hard part in it.
Yes.
Yeah. So, I mean, do you remember the proof or?
Yes, sir. A source node would always exist. And then once we know that a source node always exists, we can keep removing edges while moving to the next vertex. If we keep on doing this, the property of being a directed acyclic graph is still invariant. It's not changing. So eventually what we'll get is a sequence of sorted topological sort.
Correct. Yeah. So basically, you do an induction on this stuff. Okay. So this is something that I think is not, so I will leave it as again an exercise. So what about the rest of you? Are you guys comfortable? Okay, maybe we should try to take a shot at it. Okay, prove that this way of doing it will give you a topological sort of the algorithm. If you have already seen it, perfectly fine. If you don't, then go and prove it. So this is something that will be covered in the tutorial if you have not done it. But I want you guys to at least try it out for some time. Try to prove it, that why does this DFS, the fan ordering this vertices based on the finishing time, gives us a topological sort. Okay, so this will help. Yeah.
Sir, I would like to read more about search. Can you recommend resources?
Oh, these things, this kind of stuffs. These things
No,
are
no,
there
no.
in any
Just-
book.
Oh, okay, understood.
Any book,
Understood.
any algorithm book will have DFS and BFS, topological sort, all of this very well covered.
Okay, understood.
Any algorithm book you pick up. Yes. In fact, I would really encourage you guys to go and pick up your favorite algorithm book or whatever algorithm book you find in your hand. I have recommended Kleinberg, Tardos, or CLR in the book, but you can talk about anything. Okay. Yeah. And yeah. So you can pick up any book, and that would be that will have that full details of this DFS and how we want to and how the proof of correctness of DFS, correctness of topological sort, and all of this. Okay? I really encourage you guys to do it. Not encourage, but I ask you guys to go and read it. Okay? You will also see how to write the proofs formally there. Okay, so this will give you a topological sort, and that is how that's a very powerful application of this DFS technique. Now, so I would so DFS is one particular way of doing a traversal. Okay, and we have seen just now. There's another way of doing a traversal. I will not do it in formally today. I will do it later on. But this is called the breadth first search. Now, I will just give you a idea about how this is done. Okay, what is the algorithm? So say you have a exam, right? In that exam, you have not exam in ISI, say you have say 4 courses or 5 courses going, right? So there is an algorithms, there is maybe automata, there is computer organization, there is possibly optimization, there's machine learning. So these 5 courses are going on. There is a syllabus for each of them. So when you prepare for your exams, how will you prepare? There are 2 ways of doing it, which people usually do. Right? So the DFS, what it says is that it's like you pick up one problem, one subject, say algorithms, and you go through the whole syllabus of algorithms. Once you're done with the whole syllabus of algorithms, then you kind of start the next one. Okay, what is the next? Okay, good. I have say computer organization. Okay, I'm now going to go over the whole syllabus of computer organization. Then I take the next one, say machine learning. Okay, I'll do the whole syllabus of machine learning. Then I go for, so you kind of go into depths. You take one subject, go into depths, learn as much as you need to learn, and then move back. There's a contrary way of doing it, which is how we kind of teach the courses, so basically how things happen, right? Which is that, okay, first let's learn the first chapter of all these 5 chapters of 5 subjects. first learned, say, the first chapter of algorithms, the first chapter of machine learning, first chapter of computer animation, first chapter of automata, and so on. Then when we are done, then they look at the second chapter. Then you go into third chapter, right? So that is a breadth first search. You're covering breadth. You're trying to cover as much. So maybe you're not going into depth of the same subject in one go, but you're covering it in terms of, I mean, first you cover all ith chapters, and then you go to the I+1 chapter for something. Okay, so that is the idea of breadth first search. So you have this depth first search and you have the breadth first search, and we have just seen depth first search. So I would like you guys to go back and think, how can you formalize breadth first search? Okay, this concept. So basically, idea is that if you have a vertex, you should look at all its immediate neighbors before going to the vertices which are possibly a bit further away. So you're starting from a vertex, you look at all the neighbors which has a distance I before going to the neighbors which are vertices which are a distance I+1. Okay, so please go back. So you have I know that they have this holidays and whatever stuff like that are there right now, and we'll meet only on Monday, so we have time for that. You have also the assignments that you have to submit, but I would still ask you guys to go back and read a little bit and think a little bit on this TFS and PFS stuff. Yes, we have done the TFS. The PFS we will do a little bit in the next class, more formally, but you also think about how we can formalize it properly. Okay, so any questions other than that? Any questions that we have? No questions whatsoever. Excellent. So let me, before I leave, yeah.
Just one query that can these processes be implemented using adjacency matrices as well? Like space complexity will be larger.
Using adjacency matrices, if you do it, you have to. It will be you can do it. Okay. You can still do it using adjacency matrices, but it would be order n square. Anyway, the input is also order n square. Okay.
Yes.
I mean, yeah. I mean, of course, you can in order n square, you can convert an adjacency matrix into adjacency list and then work on it.
Yes.
Okay. So adjacency matrix is anything that can be done in adjacency matrix list can be done with adjacency matrix with an additional that extra cost.
Okay, sir.
Okay. Okay. So before I just end today's thing, I just want to see this what is the distribution of people who are coming to this class. Let me just quickly launch this poll. Okay, I think I got the overall distribution. Okay, so thanks. So let's meet on Monday.
Thank you, sir.